It's my privilege to introduce our next speaker, Howard Nestman. Howard is a structural integrity chief engineer at Northrop Grumman, supporting advanced programs with additional roles as a designated engineering representative for the FA-18 and structural analyst lead for the F-5 T-38 program. He holds a bachelor's degree from UCSD and a master's from UCLA, both in aerospace engineering, and has 25 years of experience specializing in fatigue and damage tolerance. His career work spans major aerospace projects like the F-35, Global Hawk, and Boeing 777 freighter, among others, covering the full life cycle of aircraft design and sustainment. Please join me in welcoming Howard Nestman.
All right, so my name is Howard Nestman. We're going to walk you through a little bit of a journey here. I got asked by Craig to do a presentation on our use of HyperX. Well, I said, great, I've got a team that does HyperX, I'll have them do something and I'll go ahead and take all the credit and present it. Sure enough, the project that I was planning on using, fund got canceled, so I'd already committed to presenting, so then I had to learn the tool myself. Max was presenting me because he spent the full 6 hours, him and James, teaching me what they knew about HyperX and like the significant crash course. And then at the same time, our company decided to get rid of the FEM software I'm used to, Patran, and go with Siemens FEMAP, which isn't a problem, but now I'm learning to do two new tools in a short period of time. So with that, but either way, using this, one of the things that drew me to it immediately, and this is going off of what Paul and Don were coming up with, was in conceptual design, we're oftentimes doing trades. And we know with those trades that we're going through that there's going to be certain teams that are going to have a little bit higher priority on some of the voices. Your aero performance, configuration, survivability, those guys, they have significant input. Structures really doesn't get a whole lot of say in it, partly because the time it takes us to do our structural layouts, develop a FEM, get loads, to give back sizing updates or weight estimates isn't there. So what they typically do is they bypass us and go straight to the parametric values from our mass properties team. So the thing is we're not fast enough. So the question is, can we be fast enough? Because like I said, when weight's a consideration, these parametric values are based off similar platforms. Some of those are going back to like the 60s, not even using certain technologies, new key technologies, but also not even the same requirements. So the other thing is it requires a lot of experience and judgment, and things like structural efficiency, which is one of the things that we come up after, is really key, and they're using engineering judgment to do this. So oftentimes by the time structures comes on board in full earnest, we're stuck with that proverbial having to stuff 10 pounds into a 5-pound bag, right? But now with the shrinkflation on the bag and, growth on every requirement that's being put in there, it's like 15 pounds in a 3-pound bag. So those are the things that, we're fighting. So the question is could we go ahead and use HyperX to do some rapid trade studies in near real time, just get a rough estimate, that 80% answer where we need to know, is this design going to be better or worse, and give structures a say in those designs. So the concept that I was looking at for a trade was, hey, can I just take big bones? We don't have a model. Someone just mops up a little bit of a loft or FEM. We haven't even settled on the configuration per se, but we've got it. Could we just do a real simplified FEM, get some simplified loads, doing some of the rapid loads case, not necessarily a full survey, but we know where maybe some of our design points and criticalities will be. Go through, put it through HyperX, go through update models, load cycles, and then come out with an answer that kind of gives us an idea of what we're going to end up with as far as a weight that we can then use to feed back to mass properties to go, look, this design is better than that. So using that as a problem, one of the things that comes up on occasion is wing platforms. What type of wing platform do we want to use? So let's take a theoretical program. They're trying to decide between two types of platforms. Wing platforms. One of them is a tapered chord, and the other one's a constant chord. The idea is that, for the most part, based on my knowledge, I know that the tapered wing can be more structurally efficient, but unfortunately the parametrics aren't really set up to tell me that. They're not going to tell me it's going to be more structurally efficient other than I tell them it is, and it doesn't have saved. But let's just say there's other teams that are really pushing for that constant chord because it meets their design requirements in a better setup. So basically, I'm wondering if I can just take the basic OML that represent the structure, make a structural box real quick in a FEM for each platform that meets the requirements, and then size that structural box that will allow me to see what the structural efficiency is between the two designs and overall platform weight for at least that configuration. And I could do the box, I could do the full wing, but in this case I'm focusing on the box. So starting with this, I just need a FEM. I know there's some internal loads people in this audience. I'm not disrespecting anybody who does internal loads, but right now I just need a FEM that gives me basic load pass and basic structure. It's not going to meet the rigorous GFEM level that we're used to necessarily, but basically going through and seeing that with the tapered wing, I went through and basically put one property on there, put a property in for the chords, did everything sizing. Because what I'm really focused on is not the stress levels or anything like that. What I'm looking at is I want loads, because that's what HyperX is using. I just need something that gives me the loads and the load path. Same thing with the constant cord. You can see I use a couple different properties there, and I'll show you why in a little bit later, but basically just try to blast everything as much with quads, not focusing on where things would go, and then basically, bars for what I would consider the spar caps and stuff like that. Didn't model any ribs, didn't model in any stiffeners or anything like that. Just going to use the properties that HyperX allows me to quickly turn on. Likewise, getting loads. Once again, did it myself, so took a basic elliptical load wing distribution, which is pretty typical. You can tailor it, but if I had my option, I'd probably go through and get a loads person and go, hey, run me some quick wing planform loads for a couple basic points in the sky for comparison. Starting with basically your basic two conditions, your up bending and your down bending, using the lift, and then also having some what was based on planned inertia weights. So as you can see, we've got inertia weights that were estimated by mass properties to say this is what we think the inertial weights would be for those types of structure. So you can already see based on what the weight is for the constant cord, they're betting on constant cord being lighter. So anyways, so from that, doing a tailored thing where I basically come up with a composite load case that subtracts the lift times my accelerations minus the inertias, and then ran those as my two applicable cases. So coming back to it, one early thing is before you ever start off and doing some sizing analysis, always do your checks. So as you can see, when I start with no internal structure, you can see what I end up with as far as, with right here with wings and deflections. Now, granted, it's only using loads. It does use moments. Maybe it gets away with, but if I went and showed my boss this, he'd be like, are you nuts? There's no way we're doing this. It's just, that's not going to matter. So I said, okay, I can put in some basic internal structure just to give me some sense. And we'll talk about why this is actually a good thing later. But I put in some ribs at a fairly large spacing, and then once I go back and do the deflections, you can see, hey, I got the same thing. Now, moving down to the constant cord wing, you can see that, hey, you can see why I already had some thickness here because I was already getting some of these excessive deflections, and we tried playing with boundary conditions and things like that to do it. But we decided, hey, add a rim, now they're smaller, they're more localized. The weight impact of that small little panel isn't going to be the biggest difference to it, but I can still go through and use HyperX and size everything that I need to go size. So moving on. So doing the structural sizing in HyperX. So what I'm looking to do is basically do the initial design following just basically a metallic skin stringer design. Not trying to do the optimization of composites or things like that, which I could. I want an apples to apples. What's it going to tell me? Because I could take and do the full tray study later once I down select to a design, but at least early setup to go through and do it this way. So the sizing studies were performed using a couple methods. I started off with an orthogrid where the zero was oriented basically along the span, but I quickly realized, that's not how we're going to do it. This is so thick, so size, we're not going to get the big giant plate that we're going to go stick with sheet metal and stringer design, so I went with a Fasten Z design. Could have done any other, but I know that's a typical industry practice. Most Boeing commercial wings are built that way, or at least in the past, not necessarily the new ones, but in the past they were done that. And then what I did is I basically used the buckling span in the X to kind of tell me where do my ribs want to be? What's my buckling distance? Because I'm expecting these to be stability sized. So I want to know where that's going to help me. And then at the same time, I varied my stiffener height. So I knew I had a Z stiffener, but I let it float saying, okay, if these are thin enough, maybe I can go through and machine them for various heights as they go along. And then I also went through and eventually set them at a specific sizing as I learned as I went through this. So not only am I learning this tool, I'm also learning what it's giving me as feedback and updating my process and trade as I go through and do this. So either way, as you can see, both of my boxes here are broken down into the structural elements. One thing, because I did get some peak loading, I did break this zone here into 3 zones locally just to go through. I used basically average sizing for the wings and then peak loading for everything else just to size it. So moving on, what do the results come out? So basically going through the design for the 2.25 or less size stiffener, you can see right now where I started. For 64-inch rib spacing, I was getting weight about 5,100 pounds for this wing. When I said, hey, no, I'm going to use buckling spans of 48 inches instead, all of a sudden I ended up losing over 1,000 pounds. So quite a significance in stability margins just in that, in size. So, and I'm only adjusting the buckling span in theory for the wings itself, or the skins themselves. Oh, actually, and actually all zones. But then when I go to 32 inches, you can see that I lose less than 100 pounds. You know, I'm starting to drop off where I'm losing weight. And then the same thing with 24 inches, you can see that I lose 8 pounds, indicating that I'm no longer stability size. I'm kind of getting into the strength sizing realm for my wing itself. And because all the loads didn't change, none of the substructure itself, really, the items such as the spars and the ribs weren't really being affected by the change in those buckling lengths. So next item. So coming up with a constant cord, doing the same exact thing, assuming an all-aluminum structure, but this time I'd noticed because I did 2¼ inches and 3½, I'm going to go 3½ just for this because that gave me the best results. And as you can see, doing that, I am already 500 pounds heavier than my tapered wing at 64-inch spacing. And when I just dropped to 32 inches, dropped the spacing in half, I'm only losing less than 200 pounds. And likewise, if I follow that through for 24 inches buckling span and 16 inches, you can see how quickly, you know, little difference there is between the loads. So basically what it's telling me is, once again, that this really isn't sized by stability. And when I go look at my criterion report between the two, you can kind of see this. So now I'm using the 3½, so that way it's apples to apples between the two. And as you can see, basically everything along the top skins are sized by, you know, local buckling or Johnson-Euler buckling. And then when we come over here to the constant cord, you can see here we start off, these two are sized by strength, but as I move down to the smaller rib spacing, you can see this is strength. By the time that you get in here, you see it's mostly strength driven in the realm. So the thing is you're not going to see that driven because changing my ribs aren't spacing. But like I said, right now, everything I'm doing is based on just changing the buckling span, not changing my FEM, not rerunning loads, not building a new model, trying to do this fast. So when we come back and look at those weight trends, you can see here, the top line, the total weight for the constant cord wing, it's pretty flat. So you can see that the difference between span here, cutting that span in half, didn't do much on the weight. But when we see right here for the 2½-inch cord that you see, hey, a big drop here, and then it basically follows out of the 3½-inch cord. But then the green line here, which is my 3½-inch high stiffener on my tapered wing, you can see that it's significantly lower, and then it basically follows these two. So as you can kind of see, both the 3½-inch high stiffener tapered and the constant cord are both basically sized by strength when we kind of get into that realm. You know, the stability sizing of it isn't much different than the strength sizing. So, but one thing's missing because, like I said, this is a true weight study, and I'm pulling out weights out of HyperX. When I pull it out of HyperX, what I'm missing is my ribs. So I need to figure out a way to add my ribs back in. Now I can go create new FEMs, redo my rib spacings, things like that. But I'm like, well, I can take what the weights of coming out of HyperX are for my weights for both of those and go, okay, what's my trend line for those? And so taking those trend lines that I'm using right now, I'm going to go use those trend lines to figure out what the composite weight would be. So when I go through and do that composite weight assessment, what you can see right now from a wing optimization here is now this is the weight coming from HyperX plus the additional ribs if there were some. So you can see here where my constant cord is, when I start adding additional ribs, it's no longer flat. You see a curve going up. But likewise, when you see here the 2¼ when I add my weights, I get the drop off like we had before, but then it starts to slope up rapidly. But with that 3½-inch where I was sized by stability, you can see right now that actually shows me to be my lightest weight. Now, 64-inch rib spacing is pretty large. Yes, I know that. I'm also idolizing my model, but I wasn't determined on that. But either way, I can tell if, regardless of the number of ribs I add or my spacing, I'm going to be much better than a constant cord on a significant level. So with that, the question was, all right, how real is that assumption? So what I did do was, since I already had a 64-inch rib spacing, you go add in some intermediate ribs. And as you can see, I've got them. So same basic FEM, just intermediate ribs, same properties that I had originally, just did it, went through and ran it. And I ran it for both the 2¼ inch and 3½-inch assumptions. This was less than 2 3/4 or 2¼ less or less. This was just set constant at 3½. So I'm assuming an extruded stiffener that would be basically constant. So you can see I actually came out with the exact same weight. So, and if we go back a slide, you can kind of see with this point, they are right there with each other from a weight. So it's not surprising that they do it. But then what I decided was, well, the one thing I haven't done is do the property updates. So I went through and did my property updates. And when I went through and did that, coming over here, and I jumped it down, you can see that basically the overall weight came out to be almost exactly the same. So even though I took it, and this isn't too surprising, because what this is basically a single load path structure. So your load distribution amongst it isn't going to be that different, which this model is confirming with me. And then the thing is, but if I were doing something probably with a little bit more redundant structure, fuselage or something along those lines where load paths can shift, you might need to do a couple more of those sizing updates. But either way, I've now gone through and done my sizing and saying, hey, this works. So how does this compare when I compare the three different methods? So one of them is using the course mass, with the estimated rib weights. So that would be my 64 inches right here. And then at the same time, what happens when I just do the 32-inch rib spacing, the updated model for the 3.5-inch stringer, and then updating the rib properties as well. So you can see the trends of the different items up here, how they trended. You can see that really with the 32-inch rib updates that I got some funky rib weights. Recognized a lot of that had to do with the caps. So that was the thing, is there was a lesson learned that the buckling and stability strength of those caps, having to strain with them, we're going to pick up more load, so therefore they became heavier. But anyways, when it comes out, the estimated weight that I had was about 4,388 pounds for the 64-inch rib spacing. So with that, when I go and update to the 32-inch rib spacing and run through my sizing, I get 4,428 pounds. I have 40-pound difference between them, and then basically a 41-pound difference between that and my other model with the updated properties. So in essence, that's less than a 1% difference. So like I said, I'm looking for the 80% answer, and I got within 1% of what my rough idea would be, but good enough for me to do a comparison to go back and say, hey, survivability guys, shove it. I want my taper cord. You don't get your constant cord, things like that. So I feel like I now have it. So to do this, basically getting the FEM, or getting a mesh, making the FEM, doing HyperX, and running through this, it literally was done in the course of a week. So it took me a lot longer because, like I said, I had to learn software. I had to use some of James' time. I had to use some of Max's time. I had some friends that were using the software, called them, emails. So it did take me longer, but if I were to do it now, knowing what I know, and I don't even know the full capability, I'd be able to do this way, way faster. So, but one of the things that I wanted to highlight from it was basically it does really give a good sense of what the weight will be for, spread estimated weights and, panel theory and stuff like that from a simple layout. So we're able to do something fairly quickly, get an age, and it also helps settle that age-old question of what's the optimal spacing. I've run on programs where people are like, it's going to take me 2 months to go through and do all these studies to do something like this, or a trade study, and it's like, it doesn't. If you stick with your similar strain of thought, that's going to end up driving you down. Yeah, it's going to take months, but now I can answer that question in a matter of days. And like I said, it can be helped to make decisions quickly. It also allows us to provide impacts from a structure standpoint in the initial design. Those MDAO figures, when they come out and going, hey, wait, here's how critical it is. Yes, I think I can drive towards that weight. So obviously with a few other people, you could do more of the fuselage and the outer wing, stuff like that. But the data-oriented approach really allows us to correct for inaccuracies in mass properties. So we're no longer held on the structure side, being held to mass properties, who liable to tell you that they're great, and when you don't make your weight targets, they always blame the structures guys. It's like, my parametric model said you would be this weight and you're not. Well, what Paul was showing earlier, saying, hey, here's the typical design curves, but the thing is that that's based off of what an estimated weight would be from parametric values to start with, and then once you start getting that data gets in, we're already basically, hand-tied in a, fist competition, or basically one leg behind our back, stuff like that. So anyways, we're really struggling. So now we actually have something that we can actually go into and say, hey, this is actually going to be better design. We can trade these other requirements from other teams and go from there. So, and then like I said, they can be performed much desired, much earlier. And as mentioned, the longer we can get away from the mass properties, parametric values, the better off we would be. So with that, like I said, going to this, it now allows us to, move to our bottoms-up weight much, much earlier. So, especially in weight-sensitive designs. All right, any questions?
So do you think there's a taper that'll give you equal strength and stability margins, this optimal?
That's what I was going for. I was looking for basically the weight of, the ribs are added basically mostly for stability, not for strength. So the idea was there was going to be some happy medium in between where the rib spacing would give me a good stability, help keep my stability margins, high enough, and then basically get close to equal to where my strength value is. It's not necessarily what I was shooting for. It was kind of from a weight standpoint. But like I said, there's a lot of knobs there that we could turn to go through. But the key idea for me was, can I compare two configurations quickly to kind of help give structures a voice?
Your workflow was sort of framed as multiple options are being considered, and one or more would be very difficult for structures to work with. Do you see HyperX being used in kind of the opposite way, where maybe design has one configuration they really like and structures has a few ideas for different ones, and you could use it to quickly explore which of those might be as competitive or more competitive?
That's the reason I got the software in the first place. Because I was fighting that exact thing, where we had some people going, look at every other craft, it's designed like this, and I said, well, no, this is more structurally efficient, and I got it to basically prove that out. So that was one of the reasons why I wanted the software, was because I knew that the people doing the trades wouldn't do it fast enough to be unbiased. So I needed something, and I knew that there was software out there that could do it quickly enough.
You briefly mentioned the rib caps getting larger and sizing up, and then kind of that weight cycle. I'm curious if you could elaborate on that lesson learned, because I think that's something that we've experienced as well.
Yeah, so with any sort of wing design, everything was modeled as a bar. So based on it having it modeled as a bar, most of the ribs, if I'm going to put stringers in, I'm going to keep my stringers continuous, and I'm going to break up the lower cap of my rib, because what it's really doing is trying to keep the shape of it, but also be a shear flow. So with that, I don't need a constant chord. But since I did, what happens is when the wing flexed up or moved with it, the cap would bend with it, and it was those bending loads that were causing weight to go up. We've seen that in other models too, where someone modeled it. If you modeled it as a rod, it doesn't take bending, and hey, that's the way they analyzed it by hand. We put it in HyperX. All of a sudden, we see much higher caps because we were picking up bending. But it wasn't because it was bending, it was because it was rigidly connected to the skin. So when the skin flexed a little bit, that cap bent in its strong axis. So, and then that was affecting sizing. So it made us rethink how we were going to do some attachments and stuff like that.